please welcome Mr. Nickil Shah, Energy Innovation Center, to please come up on the dais and share your presentation with us and the audience. Over to you, Mr. Shah.
Thank you for the opportunity for speaking at this wonderful trade event, the first India Battery Show. My name is Nikhil, and I'm a PhD student from the University of Warwick, and I'm here to show you a little bit of a masterclass in materials characterization, our capabilities for what we have at Warwick University and our pilot line. So just a quick outline of my talk. So Warwick University is based in the heart of the Midlands in the United Kingdom. And I'm going to explain our role in the UK-India battery ecosystem, our cutting-edge battery capabilities and characterization techniques that we have. And then I'm going to be explaining a couple of the papers we've just been published going from powder to pouch and an academic understanding of our industry format cells. So firstly, WMG key partners. Academia and business are so important in terms of collaboration. Collaboration is what drives research and innovation. My supervisor is one of the co-leads of the Faraday Institution, which is the largest research consortium in the UK. So he is co-lead of the degradation and the future cap projects. And Warwick University have many collaborators and universities that we partner with across the country. I'm sure you'll recognize some of the names of these universities. We are also closely partnered with a lot of government institutions and closely funded with many institutions across the UK. So moving on to our scale and capabilities, and where does Warwick actually sit within the battery research ecosystem? Warwick sits in the technology readiness level of 1 to 4. So we are able to go all the way from our principal materials all the way through to analysis, analytical experiments, and validation requirements. And then we also peek into the industry of technology readiness level 5, where we are collaborating with UK Battery Innovation Center to upscale our facilities to help transition the future of an energy transition. The last stage is the application of these large gigawatt factories. Now, we've heard a lot about gigawatt hours and gigawatt factories in all the presentations, but what does this actually translate to? So Envision in the UK have a 10 gigawatt hour target at the moment. And this translates roughly to about 160,000 to 170,000 electric vehicles. Very recently, the UK battery ecosystem announced a collaboration with Tata and JLR to build a 40 gigawatt hour factory in the UK. And Warwick University is closely placed in collaboration with JLR to analyze and share and trade information. So what do we actually have at our facilities? So a quick overview. Why Warwick is so well placed is that we have key control through all of these activities. So we can go from the material solvent all the way to the slurry mixing, the coating, the drying, calendaring, the cutting, the stacking, the welding, the filling, the sealing, and the formation and aging. Now, we are very well placed in our pilot line as we've modified our pilot line specifically to have a dry air feed. And a dry air feed is so important for battery material synthesis with especially high nickel content material, which is very moisture sensitive. So please do scan here if you would like a virtual tour of our laboratories. We also have a dry room facility, and I'm sure you've all seen some dry room capabilities and facilities that have been advertised at this trade show. And we have our very own provided by Munters. So what are our cutting-edge pilot line capabilities? And I explained this dry air feed, and what does it look like? Well, this is a CAD image of our dry air room, and you can see up here that we have a dry air feed pipe which feeds directly into our pilot line coating. And we have the capability roughly every year of about 50 megawatt hours. So what does this actually look like? Well, this is our pilot line. Here are our 3 drying ovens. This is where the material is enters into the pilot line, and it's coated all the way along this reel. This is the dry air feed, that pipes in dry air from our dry room to have accurate humidity control over all of our materials. So a little video of showing the entire process. So we start off with mixing our powders. This is on the 1 liter scale, but we also have a 10 liter mixer as well. And we also have thermal control, so you can see a temperature probe that regulates the temperature through liquid cooling. Then we also modify the solvent addition to ensure that proper rheology is ensured for conclusive coating and uniform distribution across the current collector. Then we degas our solutions, and subsequently, using a peristaltic pump, we coat onto our pilot line, and we have MISAR sensors, which I'm sure you've also heard of in previous talks, to make sure and ensure that the thickness of our coating is uniform, and this uses ultrasonic capabilities. We can also perform visual inspections to ensure that there are no defects on our material. This can coat about 100 meters of material throughout a day. So, what is the purpose of the dry air feed and the wet air feed? Well, now this is a little bit of an electrochemistry in-depth analysis. So what does this mean? Well, this is a dq/dV plot, and if we take the mathematical integral of the area underneath the top half of the curve, we get the charging capabilities of our battery. So the bigger the area, the larger the amount of capacity. Now we can see here with the two formation cycles that the dry air feed sample looks very good. They line on top of one another, which shows good reversibility. If we compare this to an industry format cell, we can see directly that our dry air feed cells line up exactly to industrial coatings, if not even better. Comparing this to a wet coating, and why do we need good humidity control in our pilot line? Well, you can see here that the first two cycles don't even align. They're also shorter in terms of area, indicating a lower capacity. So the humid air feed, which we've also coated in our pilot line whilst turning off the dry air feed, indicates that we require good humidity control to produce high-level, high-quality cells. So, what did we do with these cells when we coated them, and what other capabilities do we have at Warwick? Well, we can go all the way into the SEM images and look at the powder on a microscopic scale. So this is 3,500 times magnification. And we also have a fib SEM, where we can selectively target individual particles and cut into them to see what the particles are like inside. Now, not only can we do this on powder, but we have the capabilities of doing this on an entire coating. So you can see here, this is a single-sided coating. We have our current collector at the base, and we have our material. Now, this is 1000x magnification, and if we want to look further at the distribution of the binder and the coating and the additives, we can also go to high-resolution images and cross-section our particles before and after cycling our cells. So please do scan here if you would like. Please do scan here if you would like to see some of our other facilities and have a look into what you can collaborate with us. So, going into the paper and our publication. So this is the exciting stuff. So, I took these pilot line cells and I built a single-layered pouch cell material. And why we built a single-layered pouch cell material was in order to facilitate X-rays to pass through this material without having any uncompromised cell on our structure. Now, these are industry-relevant format cells, and we then compared these to industry-relevant life-on material, which the Faraday Institution is working with very closely. We then had a look at the electrochemistry of both the cells, and they align almost identically, and the capacity fade is very similar. And we also had a look at the XRD, indicating that both the materials are atomically identical. Now, what did we do with this operando XRD measurement, you ask? So, we took these operando XRD measurements and we looked at the electrochemistry. We observed that at cycle 1, the electrochemistry is good. After 101 cycles, the electrochemistry drops off a little bit in both cases. What we see is an IR drop and a kinetics drop, so these are related to degradation mechanisms within the cell. And then we had a look at the operando technique itself. So, what do these graphs actually mean? Well, our cathode material is somewhat like an elastic band. As you charge up, that elastic band expands. And as you discharge your material, the elastic band contracts again. So we start from the top, we expand to the peak of charge, and then we contract to the bottom of charge. And what does this actually tell us? Well, it tells us how our material is allowing lithium to come in and out of our cathode. And this is very important for things like fast rate capabilities and understanding material degradation. We can also look at the graphite itself and how the graphite allows the lithium to expand and contract and hold charge within the material. So we can see here that on the first cycle, the graphite is expanding nicely. And after 101 cycles, our LiC6 peak here shrinks, indicating that the graphite has less capability of containing the lithium within the structure. So, how do we actually quantify these measurements, and what do we actually see atomically? Now, I mentioned that we can do atomic level understanding, and I explained that we get our expansion and contraction of our material, so that's in the 003 plane. And our lithium sits here, our transition metal layers sit here, so our nickel, manganese, cobalt, and our oxygens are highlighted in the red. NMC materials and transition metal layered oxides have a very big problem with oxygen loss. So this technique allows us to fully understand where this might be arising from. Now, if we go into the mathematical equations of what our capacities are, we can see here with the graphite calculation that our calculation of acceptance of total capacity is 372 milliamp hours per gram. Using this same equation, we can then calculate what our theoretical capacities of our cathode materials are. And we can also track these changes, as I explained with the 002 plane before in the graphite material, of how much lithium can go in and out of our graphite. And this is known as graphite staging. This paper is now available on the ChemRiv archive as an open access journal, so please do scan this QR code and have a read of our work. So, what else can we do with this material, and what have we actually seen? Well, we went beyond that C-lattice collapse. We went beyond the atomic level contractions, and what we saw in our material is after 2 cycles, there's no cracking, so we have large statistics here. And we went even further, and after 102 cycles, we saw there was some carbon segregation, but there was no cracking within the materials. Now, why do I say this cracking is so important? Well, in polycrystalline material versus the single crystalline material I've demonstrated, cracking induces a larger surface area into our materials, which allows for more degradation pathways in our reactions, reaction mechanisms in our cells. So in another publication that we have also presented, so this is a cross-sectional image first of the single crystal particle after 102 cycles, and we can see throughout the entire material there is no cracking in any of the material. Moving forward into our next, on our latest publication that is now submitted, we can see here after 500 cycles we get cracking of the polycrystalline particles. And if we look atomically at the pristine material, there is no cracking intragranularly on these particles. If we compare this to the single crystal molecules after 500 cycles, again, we can see here that the electrochemistry aligns very nicely, as I explained before, and there is no cracking in the particles. So why work with Warwick? Well, we can do a forensic understanding, so we can tear down cells, and we can use high-level techniques such as scanning electron microscopy, X-ray photoelectron spectroscopy, absorption spectroscopy, and diffraction and surface area measurements. Our non-teardown studies, as I've just demonstrated in our recent paper, involve operando techniques. And may I just add, these are uncompromised industry format cells. So, for our concluding remarks and how we actually do these measurements and what instruments we use. So, we can synthesize uncompromised operando cells and having complete control from the powders, from the crystals, all the way to the cells through every process in industry-like cells using a multitude of chemistries. And we use chemistries such as LFP, we are branching into the LMFP, NMC, and even nickel-rich LNO materials, so 100% nickel materials. So how do we actually perform these X-ray measurements? Well, here is an image of our diffractometer with a panelytical empyrean, and we use a molybdenum X-ray source to pass through the pouch cell, and this pouch cell is connected to a potentiostat, and we use the biologic potentiostat systems. Now, the X-ray absorption spectroscopy to track chemical changes in our cell to look at charge compensation. This is our Zanes measurements. And what we have is at every stage, we have our cell build, formation, our cycle, and we have control over every single stage in our material. So, research would be impossible without collaboration. So I'd just like to say thank you to my professors and a few of the engineers who've helped really facilitate this work, which this work would have been impossible without them. And with that, thank you for listening, and a little quote from Helen Keller. So alone, we can do so little, and together, we can do so much. Thank you for listening.
Thank you so much, Mr. Shah, for such a detailed presentation. Any questions for Mr. Shah? Anyone from the audience, if any questions?
Hi, Nikhil. Thank you so much. It's mind-boggling to see what you're doing on the crystal side. My query is, we keep seeing a lot of such papers. What is happening on the commercial front? Do you actually see industry adopting this in the short term? Or is it something that will take some time for the anode side graphite materials that you would, structure that you were talking about? Do you see any industrial application very soon? Are you collaborating with industry to apply this?
Sure, a very nice question as well. We are closely collaborating with industries such as BMW, JLR, and Nissan at the moment in our facilities. And as well as Tesla at the moment are using chemistries such as LFP all the way through to the NMC level stage. And they're also using graphite in their materials for their anode side. So, no problem. Sorry.
Thank you so much. May I please extend a token of appreciation on behalf of Informa Markets to Mr. Shah.